Hello and welcome. In Six Sigma, we make use of both descriptive and inferential statistics. Descriptive statistics are summary measures that describe, show, or summarize the characteristics of data in a meaningful way. In contrast, inferential statistics is a set of techniques used to draw conclusions and make generalizations, predictions, or decisions about a population based on information and data obtained from a sample. Studying an entire population isn't normally practical or possible. Instead, inferential statistics allows us to collect and analyze random samples of the population to gain a better understanding of its behavior. One of the most important characteristics and prerequisites of inferential statistics is the importance of being able to draw random, unbiased samples from the population. This means that every data point within the overall population has the same chance of being selected. If we don't randomize, we may add bias to the study, skewing our results and limiting our ability to understand how the population behaves. Well, let's review some tips to help you succeed with the sampling process. First, when collecting random data, do so over a wide time frame, especially if we're sampling from a repetitive process, such as a production line. In other words, if a team collects parts to measure from an assembly line, they should do so throughout the day at different times and, if possible, over the course of several days and weeks. Second, our processes should be stable and in control before random data is collected. We can use data visualization, like the time series chart, to help us understand how stable and consistent our processes are. If we see wild spikes, we should focus on stabilizing the process before attempting any hypothesis test. In situations where we can't collect data over a long period of time, we can make statistical inferences from short-term data as long as this process is in control and remains in control. And third, we want to avoid any bias in our sampling methods by choosing the appropriate technique. Let's review a few of the most popular sampling techniques that we can use in many data collection situations. In simple random sampling, all samples within a particular population have an equal chance of being selected. For example, let's assume we're attempting to survey students at a high school. We want to ask students in grades 9 through 12 to rate their teachers. If we wanted to sample 300 students from a high school consisting of a total population of 1,200 students, we could put all 1,200 names in a hat and pull out 300 names. Randomly pulling 300 names from a hat is an example of simple random sampling. Next, we have stratified sampling, which involves selecting samples from a number of groups, or strata, within the overall population. Let's go back to our high school example to illustrate this. There are 400 students in grade 9, but only 200 students in grade 12. In this situation, even though all students have an equal chance of being selected, since there are twice as many students in grade 9, the odds of more of them being randomly selected are high. This could lead to a potential bias in the study. Students in grade 12 with 4 years of high school experience could have very different opinions of their teachers compared to grade 9 students who are new to the high school. So if more grade 9 students are sampled, our results may be biased. A stratified sampling approach could involve 4 hats instead of 1, with all grade 9 student names inside it, as well as hats with all grade 10, 11, and 12 student names inside them. Our strata in this example would be grade levels. We use systematic sampling to select members at regular intervals from a list of the population, often during a real-time operation. For example, a production process may inspect every 10th piece to check for quality defects. In cluster sampling, we divide the population into naturally occurring groups or clusters and randomly select some clusters to sample. For example, we may group a city into neighborhood clusters and randomly select 20 neighborhoods. Then we can collect data from every household in these selected neighborhoods. Rational subgrouping divides the population into subgroups based on relevant characteristics and selects a representative sample from each subgroup. For example, we may segment our customer base into subgroups based on income level, family size, and product usage habits, and then randomly select a representative sample from each subgroup. It's important to think through the different sampling methods and strategies so that we identify the one or ones that will ensure we collect representative data. That wraps up our review of inferential statistics and sampling. We'll see you soon.